Hey guys, welcome to another edition of Calculus Online. Again, brought to you by Patio Productions as I report to you from my backyard. So ladies and gents, I thought we would just do a quick video that goes over the answers to the quiz. Hopefully you were able to already take said quiz. I'm not really going to walk you through the steps, just kind of like show you the answers and just give little verbal tips explaining how to do it. And then, of course, if you have extra questions, you can go ahead and just come catch me during office hours. So this group quiz will round out our information for our chapter 11. And then starting next week, we'll start reviewing for the AP and practicing lots and lots of free response questions. Me and Mrs. Bright are working on how that's going to look. But for now, let's get to this and finish it up, okay? So I'm going to go ahead and I'm going to pull up. I decided to just take a picture of the answers to the quiz, and then when I do that, I'm going to I just kind of put them into a PowerPoint. I thought that would be easy to do, and so that's what we're going to do. So here is our answers to the group quiz. I'm running my own soundboard today, guys. It's complicated. Okay, so here we go. So question number 1 asks us to gives us a curve that's defined parametrically. And we know that if we're going to find dy dx, we have to do dy dt over dx dt. So I'm just doing each of those derivatives. I get a t squared over t minus 9. This right here cannot be simplified. If it could, I would do that. And then when we are asked to do the second derivative, you're supposed to do the derivative of the first derivative, which involves not a chain rule, just seriously, I said the wrong thing, which involves a quotient rule and then putting it over the derivative of the x guy. And so the x guy, like denominator, and the quotient rules denominator get to do a little combo, and then we get to like combine the top, and it makes a beautiful, beautiful, beautiful answer. So that nothing else can simplify, and those are your answers to question 1. Okay. Question 2 asks us to find the points at which the tangent line, which is defined parametrically, we've got our x guy and our y guy, is horizontal. Okay. So if you're thinking about a horizontal line, that means that the line has a slope that's 0, and the way to get a fraction to turn into 0 would be if there's a 0 on the top. So we really only need to worry about the top part of our derivative, which is dy dt, and set that guy equal to 0. So that's exactly what I did. I only took, let me see if I can grab a marker here. Okay. I only took the y guy right here, and the y guy is what I took the derivative of and then set that equal to 0. I got 2 values right here. T is positive and -1, and then I plugged both of those up at t equals positive 1. I plugged it in for the x guy and the y guy, and you actually get one answer, and then for t being -1, I plug it into the x guy and the y guy, and so the 2 coordinates are at 6, -2/3, and then 8, +2/3. That would be number 2. Okay. Number 3 asks us to find the length of the parametric curve. I kind of just wanted you to just do it, right? And so the formula for the length of a parametric curve is you take the integral, and then you have your 2 limits of integration, which in this case are 0 and pi. And then you're supposed to take the derivative. That is a very common mistake. Oopsie daisies. Is for people to not take the derivative. So I took the derivative of each of these guys and squared them. So the derivative of the 3 sine t is 3 cosine t. The derivative of 3 cosine t is -3 sine of t. I squared each of those. If you just sort of like all of this work right here separately and then shoved it in the square root, that's totally fine with me. But this one actually simplified so nice, like not even kidding. It literally just turned out to be the integral of 3. That was it, the square root of 9. You got to end up having a cosine squared and a sine squared, canceled to be 1. It was gorgeous, the end. Okay, example number 4 says we're doing a particle moving in a path, and I really think this was not meant to be hard. They gave you flat out the position function. And so when they give you the position function, the velocity vector is just take the derivatives, acceleration vector, the derivative of that, derivative of the velocity vector, So the velocity is vector parentheses, -5 sine of t, comma 9 cosine t. The acceleration vector is -5 cosine t and comma -9 sine t. Then it asks for the speed at a particular t value right here. So speed, remember, is what we call the absolute value of the vectors, but we're in vector land, so it really just means that we want to take the Pythagorean theorem. So what I did is I plugged in pi/4 to the velocity vector. I got 2 values, and then I went ahead and found the magnitude of that. So by doing that, I do the Pythagorean theorem, and it turns out to be about rad 53. Okay. The last question on the page says, given the velocity vector. So notice, guys, this time we're starting with the velocity vector. On this previous one, we started with the position vector, right? So we're starting with a different guy. So this one, we're starting with the velocity vector, right? It says find the position of the particle at t equals 2. If you know you have your initial condition. So here's the initial condition right here of 2, 6. So the way that we're supposed to find a final position is you take your initial position, which we know is 2, 6, and then you add the displacement. When we're talking about a vector and we're doing the displacement, you basically just do the integral of each guy over the course of what the interval is. And so we're talking about starting at time 0 to time 2. So you can see each of these integrals goes from 0 to 2, and I just take the antiderivative of each. I evaluate both of them. You can kind of see my work there. And then it ends up being that the displacement vector is 4, 2. So I added 4, 2 to 2, 6, and I get a coordinate of 6, 8. Okay, part B says, what's the total distance traveled? I did not want you to solve this one. It would have just been in your graphing calculator anyway to make it evaluated. I just wanted you to set up the integral. So the integral, if you want total distance traveled is simply the integral from 0 to 3, this guy said, and then you basically just do the magnitude of the velocity vector. So these values in here are literally just from the velocity vector. There's no derivatives or anything. These guys right here are just coming into play down here directly. We're squaring each of those and plugging them in, and you're good to go. Okay, so let's go and turn this guy over. Where's my turning sound? Here it is. Turn the paper over, and let's go ahead and look at those guys on the back side. Okay, so example, question number 6. Said find the equation of a tangent line, and now they put it in polar. Okay, so this was one of the last things that we had learned. And when we do polar, you're supposed to change it into parametric. And so to do parametric, it's really hard for me to write it, but basically the x guy is the function times cosine theta, which is the r, and so you basically just put in the entire function. And then the y guy is -4 plus 8 cosine theta times sine theta. I went ahead and expanded those. And then it was just a matter of doing the derivatives, and the derivatives were not cute, but we had to just roll with it. Okay. And again, what's the most common mistake? The most common mistake is putting the x guy on top and the y guy on the bottom. So silly of you to do that if you accidentally did that. But remember, the y guy goes on top. So this is the derivative of the y guy. I just did a regular derivative for the -4 sine. But then over here, I had to do the product rule. Okay, so I had to do the product rule on that part. I filled those guys in. It's going to turn out cute. For the derivative of the x guy, I have 4 sine theta because we're just doing up here. And then this had a chain rule involved for the 8 cosine squared theta. And so that's why we have this sign right there. It did say, what is it at pi/2? So I'm just going to evaluate it at pi/2. I didn't even try to simplify this. I was like, no one cares. Just plug in pi/2. So I plugged in pi/2. I ended up getting a -2 for the slope. And then I had to find the coordinate, of course, right? Because we need always a slope and we need a point if we're going to write the equation of a tangent line. I just plugged in pi/2 to the x guy and pi/2 to the y guy. I got 0, -4 for my coordinate, and then boom, just like that, I have my equation of the tangent line. I would have left it as y + 4 = -2 times x - 0. You could have like distributed stuff, and so another acceptable answer is y = -2x - 4. Either one is totally fine. Okay, then I asked you to practice the polar areas, okay? And every single one of these is just a teeny little bit different, even though we're starting with the exact same pictures. So there was a circle and a cardioid. Okay, so I just kind of drew those by hand, and then each question was a teeny little bit different. So for part A, it says shared by the circle and the cardioid. There is actually like so many different ways that you could get this guy, okay? And so I tried to do all sorts of different answers, but basically you have to do the area of the semicircle. So the semicircle is this part right here. So this part right there is the semicircle part. And then you had to do the area of the bumps. You could have done an integral for the semicircle. It didn't matter, but there's some sort of an 8 pi value. And then for the bumps, what I decided to do is just to take it from a negative pi over 2, which was this value, and then do it to pi over 2. No, excuse me. JK, hold on. I decided to go from 0, a theta equals 0, to a theta. Nope, that's wrong again. A theta is negative pi over 2 to a theta equals 0, and then double it. That's what I decided to do. And then you're just squaring it. This one, remember when I draw the spikes, I'm actually going to draw these in a different color. When we're drawing the spikes and deciding like what to make the radius, this radius is just going boom, boom, boom to the circle. And then over here, when you do these guys, these are just going to the bumps. Like there's no need to do an outside minus an inside curve. It's just literally like 2 separate parts. So there was lots of choices for getting the bumps. You could have done a 1/2 from a pi to a 2 pi. You could have gone a 3 pi over 2 to a 2 pi. You could have like doubled things or not. Lots of choices. So something along that lines would have been this guy right here. Okay. And then the next guy, it said for the question B, it said inside the circle but outside the cardioid. So this was like the cute little moon shape where the moon had a nose down here on the bottom, and I think it's like super cute. And so then this one, definitely when you draw a one of the radii, and I actually have one drawn, I don't know if you can see it or not, but there's one drawn right here. There definitely is an outside curve and an inside curve. So we are going to do the subtraction version. The outside curve is the circle. The inside curve is the cardioid. Again, lots of choices for your limits of integration. You could go from a negative pi over 2 to a 0 and double it. You can do all the way from a pi to a 2 pi and keep the 1/2. You can go from 3 pi over 2 to 2 pi, lots and lots of choices. Or even then, if you're feeling jazzy, you could have also done, and I have had students do this, do the semicircle and then take away the bumps. So guys, lots of choices. But basically this guy right here, the 4 squared is the circle. Equation of the circle, and then this guy right here is your 4 plus 4 sine theta is your equation of the cardioid, squaring each one, and you have a minus. Okay, gorgeous on that. And then our last one, okay, said it flipped it, and it said inside the cardioid, but outside the circle. So you can clearly see on this one, it's even a better picture, that there is definitely like the radius coming out. This guy right here is your outside curve. This guy right here is your inside curve. And so I decided to, again, double my value. So I went from a theta equals 0 just all the way to here to a theta equals pi over 2. And then I canceled my 2 with my 1/2. If you decided to go from 0 to pi and keep the 1/2, totally fine with me. And then you have the outside curve squared and then minus the inside curve squared. So that's it, guys. So what I want you to do is on the there's a Google form also attached to this assignment. I just want to tell you, want you to tell me how many of the questions you got right and wrong. And I know that I have little like points on there. If we were doing like a real quiz, like things would be worth multiple points and there'd be partial credit. But let's just go with the 11 questions that are there. Give me a report on how you did out of that 11. Maybe you got 8 out of 11. Maybe you got 10 out of 11. Just let me know how you did. You're not getting that score in the grade book. You're just telling me what you did. And then the Google form has like 2 little questions, and it says like report on something that was really easy and then report on something that was a little bit more complicated. Okay. Or maybe that you did wrong or you had forgotten about. And so basically, guys, that is your assignment. That was it for today. Okay, so there is no homework, right? You just, we are now concluding, tying it up with a cute little bow, okay, our chapter 11 work. And then again, next week, we will start with some reviewing for the AP. So again, we're still waiting on some specific details from College Board, but we know that we're having the AP and we've got some work to do and some practice to put in. So Mrs. Bright and I are going to have some conversations and we're going to design some good practice for you guys. So that's it. Dun, 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 dun. The end. Ladies and gents, I hope you have a lovely weekend. And that is it. Bye. See you later.